Hi, this is Dr. Tech. This is for cisp440 in 2018 fall semester. This recording is about question number 3 in the final exam. So here it is in the final exam. This is question number 3. It's about transmission problems. And the idea is there are 7 data bits followed by 1 parity bit. That is kind of like an old modem standard. Um, let's see, I'm gonna pick out a highlighter here. All right. So so this is kind of the important part. There are 7 bits followed by 1 parity bit. So the purpose of the parity bit is for error checking. So if a bit is quote unquote transmitted correctly, the number of ones should be even. So there should be 0, 2, 4, 6, or 8 bits that are ones in every, um, let's see, in every 7 bit it is transmitted plus that 1 parity bit. So I give you an example as well. So if all zeros is received, then there's no detected error because 0 is an even number. On the other hand, if 0, 1, 0, 0, 0, 0, 0, 0 is received, then we have an odd number of ones in the received bit pattern, and there's a problem. So as you can see, this type of error checking is not very reliable because if you have two if you have 2 bits, if you have 2 bits that are received incorrectly, they would quote unquote cancel each other out, and as a result, the problem would not show up. It would not be detected by this parity bit mechanism. So the last paragraph says, if we assume the error rate of receiving is p, so a 1 being received as a 0 and a 0 being received as a 1 are the same and they're both p, I want you to derive the probability of a character transmitted erroneously without being detected by the parity bit. A character in this case has 7 data bits. So I want you to also show your derivation excuse me, step by step, and quote any theorems used. Okay. So what we want to do, okay, let me go ahead and write down, the text version of the answer. Okay. So the 2 things that are important in this case, the first one is to understand how many ways can a character be received erroneously but without getting detected that it was received erroneously. So we can have, let me switch back to a pencil tool. So we can have 2 error bits, 4 error bits, or 8 error bits. And remember, the number of error bits can include the parity bit itself. The parity bit can be received erroneously. So from that perspective, the 8 bits received are pretty much, there's no distinction between the 7 bits that are representing the character versus the 1 single parity bit, which is kind of used as a checksum. Okay, so if 2 error bits are erroneous, then the total number that we need to deal with here is going to be, there are 8 bits. We choose out of those 8, 2 out of those 8 bits, and then p is the error rate. So in this case, we have to have 2 to the power p to the power of 2, and that's for the bits that are received erroneously. But also at the same time, we also need to remember that there are 6 bits that are not received erroneously. So now we have, so that's basically the probability of receiving a character with 2 error bits without getting detected. 4 bits is kind of similar. 8 choose 4. p to the power of 4 times 1 minus p to the power of 4. And then what if we have all error bits? Well, then we're choosing 8 out of 8 bits that are erroneous. P to the power of 8 times 1 minus p to the power of 0. And obviously I forgot one thing. I forgot the 6. Okay, let's put the 6 here. Alright. So now we have 8 choose 6, excuse me. P to the power of 6. 1 minus p to the power of 8 minus 6, which is 2. So the idea is we have to add up these numbers together. So if you want to gotta use a more graphical way, you add up all these numbers, then it becomes the probability of receiving a character erroneously without detection by parity bit. And this is based on the binomial distribution. So binomial distribution is what we used here. So the alternative answer, if you want to be kind of express the whole thing in a more close form, is to have a summation where I is an element of 2, 4, 6, 8, and then each term is 8 choose I, p to the power of I times 1 minus p, the whole thing to the power of 8 minus I. So that will work as well. So you can either kind of use a more pictorial representation like this one, or a more mathematical notation like this one here. Both will work. So what I'll be looking for obviously is the equation or the formula itself, and also something that mentions binomial. So you can say binomial distribution, binomial theorem, which has something to do with this. Okay, but both would work. Binomial distribution or binomial theorem would work in this case. And just showing that we have 4 terms, and the summation of the 4 terms is what is important. So to assign partial credit, the use of combination is important. So that means this portion here is important, to understand that we are choosing any 2 bits out of 8, any 4 bits out of 8, any 6 bits out of 8, and any 8 bits out of 8 to be erroneous. So that part is important as well. All right, so that's it. I mean, this is one of the shorter questions, and when I'm ready to record the next question, I will let you know. I'm trying to figure out a way to right click. Okay, maybe not then. And there's no easy way for me to get back to. Oh, okay, there we go. There we go.